Hi there. In this video we're going to talk about classes and purposes of hardware-based 3D acquisition systems. Talk about contact versus non-contact, passive versus active methods. We're going to take a look at passive multiple view stereo and then look at with greater detail on the active lighting techniques, specifically active stereo, triangulation and structured lighting systems, time of flight, and LIDAR. Let's do an overview of classes and purposes of 3D acquisition systems. As you might recall from the previous lecture, 3D scanning deals with collecting data on shape and appearance properties such as color for real-world objects or scenes, effectively digitizing them. You also might know from your own experience the many names connected to technologies such as passive stereo or computer tomography or LIDAR. In today's lecture, we will overview these and many other 3D scanning technologies, provide a classification of such systems, and introduce their basic physical properties and consequences connected to these. We will further demonstrate many of these systems in action and discuss their limitations. When facing many of the modern 3D acquisition devices in exhibitions, medical facilities, or industrial labs, you may find yourself asking, how do these technologies work? And how can I make use of the shape data they produce? More importantly, can I scan any of the objects around me? And what kind of precision can I expect? 3D scanners differ by quite a number of properties. Some of these devices can be used to scan huge areas, while others are only useful for little objects. Some of them are capable of scanning translucent or reflective objects like mirrors or metals, while others cannot. Some of them provide high-frequency capture at 90 FPS, while others take minutes or even hours for the image to form. Some are affordable, while others very expensive. Let us build a small taxonomy of 3D scanning machines, inspired by a conventional classification by the pioneers Brian Curlis, Douglas Landman, and Gabriel Taubin. A variety of technologies exist for digitally acquiring the shape of 3D objects. Contact 3D scanners probe the subject through physical touch, while the object is in contact with or resting on a precision flat surface plate. Where the object to be scanned is not flat or cannot rest stably on a flat surface, it is supported and held firmly in place by a fixture. Rulers, calipers, pantographs, and more recently coordinate measuring machines are examples of such technologies. A coordinate measuring machine, or CMM, is used mostly in manufacturing and can be very precise. The disadvantage of CMMs, though, is that it requires contact with the object being scanned. Thus, scanning the object might modify or damage it, which is crucial when scanning delicate or valuable objects, such as historical artifacts. The other disadvantage of CMMs is that they're relatively slow compared to the other scanning methods. Passive 3D imaging does not aim to emit any kind of radiation, but instead relies on detecting reflected ambient radiation. These methods generally assume that the sensor simply records light that already exists in the scene. That is, the sensor is passive. In a sense, such sensors attempt to take advantage of a wealth of visual cues present in the human visual system: stereo and motion parallax, occlusion, perspective, shading, focus, and so on. Active scanners emit some kind of radiation or light and detect its reflection or radiation passing through object. Transmissive devices such as computed tomography or transmissive ultrasound, aim to record the decrease in the intensity of the radiation passing through objects. Reflective methods are another class of range scanning methods that is becoming increasingly popular. These include non-optical methods such as reflective ultrasound, radar, sonar, and MRI, active variants of passive methods such as active stereo or defocus using projected patterns, time of flight, where the scanner emits a focused pulse of laser light and waits for it to return to a sensor, or triangulation, which projects structured patterns of light and records reflectance. One question to ask is, what is the typical scale of objects that can be simultaneously sensed, and what is the common time resolution of sensing? That is, how frequently can one obtain novel measurement of the shape of the objects? This diagram roughly represents typical ranges of these parameters for a variety of sensor classes. The slowest sensors are computed tomography and coordinate measuring machines that are able to deliver one measurement of an entire object in minutes, if not hours. Time of flight, LIDAR, active stereo, and some variants of structured light systems are able to capture depth images at 30 to 100 fps. Another question is, what is the typical resolution of depth measurements, and to what extent are those sensors accurate? In other words, what kind of geometric detail will we be able to reconstruct, and how precisely? Note that for most sensors, 3D precision, meaning the accuracy of individual 3D measurements, depends both on the range of scanning and the desired 3D resolution, that is, 3D precision is not constant. CMMs and computed tomography are again the most precise methods that can deliver micrometer resolution. TOF, LIDAR, and active stereo methods are commonly less accurate, with resolution and accuracy within tens of millimeters. Structured light systems provide a compromise, being able to scan at sub-millimeter resolution with accuracy around tens or hundreds of micrometers. Most scanning methods have limitations in terms of which objects can be effectively scanned, or if they can be scanned at all. For instance, contact methods, such as coordinate measuring machines, are commonly not used with fragile or moving objects. Passive optical scanning methods, such as multiple view stereo, have troubles with reflective or transparent objects, textureless objects, such as flat white walls, or objects textured by periodic patterns. Other types of methods sometimes have more elaborate restrictions, such as time-of-flight techniques, which suffer from multipath interference effects, for instance when dealing with glass or other semi-transparent objects. Multiple technologies are able to deliver significantly different results. Among factors that differentiate between the 3D scanning methods, we view spatial scale and temporal resolution of the objects that we scan, qualitative properties of those objects, and different physical principles that we leverage while performing scanning. The methods also differ quantitatively in terms of their 3D resolution and 3D precision. Let us Clarify the difference between contact methods versus non-contact methods. Contact methods, such as touch probes, record measurements by performing a physical contact with the subject. They are commonly manual or computer-guided. For example, the coordinate measuring machines are able to position their handle or probe using an elaborate computer-guided machinery. Their common advantages are that they can be very precise down to micrometer precision, and they can also scan any solid surface, be it transparent, translucent, or reflective. They also have some disadvantages in that they cannot scale large or elongated objects, and they cannot be used, or should not be rather used, on fragile objects because they can basically damage or deform the objects. This is why such methods are rarely used with historical or cultural artifacts. In this example, a coordinate measuring machine sequentially probes the surface of the sample by sensing discrete points with a probe. This is a 3D bridge CMM, which allows probe movement along 3 axes, X, Y, and Z. Each axis has a sensor that monitors the position of the probe on that axis, typically with micrometer precision. When the probe contacts a particular location on the object, the machine samples the 3D position, thus measuring the location of one point of the object's surface as well as the three-dimensional vector of the measurement taken. The process is repeated as necessary, moving the probe each time to produce a point cloud, which describes the surface areas of interest. Let us further clarify the difference between passive methods and active methods. Non-contact optical scanners can be categorized by the degree to which controlled illumination is required. Stereoscopic imaging is one of the most widely used passive 3D imaging systems, going under a variety of names such as multiple view stereo, structure for motion, or simultaneous localization and mapping. Stereoscopy estimates the position of a 3D point by triangulation. That is, obtaining depth by intersecting 3D lines drawn from each camera's center of projection through the 3D point. This requires correspondences to be found among the various viewpoints, and is difficult for surfaces where texture is flat, periodic, or missing. To sidestep the correspondence problem, alternative methods reformulate the problem and focus on other visual cues, such as visual hulls and silhouettes. They leverage limited depth of field to only put objects at a particular depth in focus, or modify the shape of the aperture to make point spread function strongly depth-dependent. Active optical scanners overcome the correspondence problem using controlled illumination. They can project textures or coded images in visible or invisible spectrum to the target, or they can measure time that is required by the light to reach the target. In comparison to non-contact or passive method, active illumination is often more sensitive to surface material properties. Strongly reflective or translucent objects often violate assumptions made by active optical scanners, requiring additional measures to acquire such problematic subjects. Stereoscopic imaging is one of the most widely used passive 3D imaging systems, both in biology and engineering. It is very accessible as high-quality cameras are cheap and provide high-definition imagery. One may additionally use internet photo collections to build large-scale models of structures such as buildings or even entire cities. In controlled setups, multiple view reconstruction is able to deliver sub-millimeter precision by using color cameras only. The terms multiple view stereo and structure through motion are used interchangeably to refer to the pipeline in computer vision community, and simultaneous localization and mapping, or SLAM, in robotics community. So, multiple view stereo, also known as structure from motion, is the process of reconstructing 3D structure from its projections into a series of images taken from various viewpoints. It commonly starts with correspondence search, where the goal is to find scene overlap in the input images and identify projections of the same points in overlapping images. The second step performs a complicated incremental sparse reconstruction, where the goal is to find 3D camera poses for registered images and the reconstructed scene structure for a sparse subset of 3D points in the scene. Finally, dense reconstruction aims to estimate per pixel depth values, while mitigating any inconsistencies among individual estimates. At the heart of the structure from motion estimates lies the basic triangulation principle. The 2D projection of a given XYZ point is identified in each camera. We denote these by XL and YL, XR and YR for left and right cameras respectively. Commonly, images are rectified so that y-coordinates on the left and right images are the same. Using known calibration objects, the imaging properties of each camera are estimated, ultimately allowing a single 3D line to be drawn from each camera's center of projection through the 3D point. The intersection of these two lines is then used to recover the depth of the point. The quantity disparity is the difference in image location of an object, seen by the left and right cameras respectively. This quantity is inversely proportional to depth of a 3D point, given the optical parameters of the system, which follows from similar triangles. The depth can therefore be estimated using the formula in the slide. If you're interested in knowing the full detail connected to reconstruction from images using structure from motion framework, I strongly encourage you to carefully study the excellent course on multiple view geometry by Daniel Kremers from Technical University of München, who carefully describes the full SFM pipeline and the relevant geometric, algebraic, and optimization aspects. Please follow the link on the slide. This example demonstrates the reconstruction of an old Croatian city of Dubrovnik from 58,000 images acquired from Flickr. The reconstruction is sparse and features around 3.5 million points. Another example is a dense reconstruction obtained using 24 images taken from different views. The images depict a historical artifact and were taken by me personally in the city of Moscow. The reconstruction is highly detailed point cloud along with its mesh representation of the surface. As you might have noticed, multiple view stereo methods have problems where textureless or specular regions are present. This is due to the hardness of the correspondence problem. Because the method have to match between different views, it suffers when there is nothing to match between these views, or something to match that looks differently between the couple of views that you're matching. Specifically, in this example, the statue of the horse from Tanks and Temples dataset has a lot of specular regions and shiny regions, and therefore it is difficult for a correspondence algorithm to find direct correspondences between the views, which results in a number of noisy patches in the resulting reconstruction, even in state-of-the-art methods. To recap, MVS and SFM infer the geometry from light reflectance by only using color images as input. Their advantages are that they're less invasive than touch, they're basically passive, non-contact methods, and they are also comparatively fast and allow for large-scale reconstructions, including entire structures and even entire streets and cities. They have a number of disadvantages, of course, in that they have difficulty dealing with transparent, translucent, shiny or reflective objects, or objects that have flat textures, no textures, or repeated textures, due to the hardness of the correspondence task. Under some conditions, optically superimposing texture can be helpful and even required to perform efficient stereo matching. To this end, active stereo vision relies on the addition of an optical projector that is located near the stereo cameras and overlays the observed scene with a semi-random texture. The goal of this texture is to facilitate finding correspondences, in particular in the case of textureless surface like monochrome walls. When an active texture projector is available, the corresponding stereo matching technology is sometimes called unstructured light. Unstructured light systems do not require knowledge of the structure of the projected pattern, as they are used simply to generate texture, which makes image matching unambiguous. Because the technology uses dense stereo matching, the result is a dense range image. In this example scene, two semi-structured patterns with significantly different texture frequencies are being projected onto the piecewise smooth scene. As you may notice, the patterns are densely textured, photometrically consistent, meaning very little change in illumination across space may occur, and they have no repetition along the axis of matching, specifically in this case within the matching range. When the left and right images are taken from the scene with such patterns superimposed, running a simple dense stereo matching algorithm, for instance a basic correlation of these images, allows to robustly find correspondences. Note that for regions not lighted directly, one should observe no matching, and hence random matches should be expected. This is indeed what is observed behind the ball in this example, when using higher frequency patterns. An example of an active stereo device is the Intel RealSense family of depth cameras, available for the mass market at a relatively low price of around $200. Each device includes an infrared texture projector with a fixed pattern with the emission spectrum within the band of 850 to 854 nanometers, invisible to the naked human eye. The optical patterns for the D 435 projected onto a flat wall are shown in the slide, recorded by the same device. Three cameras are included, a left-right stereo pair and an additional color camera. The left-right cameras are identical 10-bit global shutter VGA monochrome cameras with a visible cut filter to block light approximately below 840 nanometers to maximize the SNR of the active texture projector. The cameras are capable of running at 30, 60, or 90 FPS. The color camera is a normal Full HD Bayer patterned rolling shutter imager. The device is smaller than a screwdriver with a 76mm baseline and features right monochrome camera, an IR projector, the left monochrome camera, and the RGB camera. We mount the sensor to be able to experiment with it. The software displays the depth images and the reconstructed meshes obtained in real time using the actual software built into the sensor. As you can see, the reconstructed meshes are quite noisy and coarse. One can view simultaneously the depth image and the reconstructed depth image and the corresponding RGB image, or overlay them for a colored depth map. The actual sensor is displayed in the scene with its orientation. One can export the actual reconstructed scene into a standalone program such as MeshLab. Unstructured light active stereo enjoys improved correspondence search and is able to work both in zero-lux environments and in broad daylight by projecting onto the scene semi-structured textures in the invisible spectrum. But this technology has its own limitations. Without a strong infrared light source such as the projector, special light bulbs, or the sun, the left-right cameras are unable to see. And the laser speckle pattern seen from the left and right images is unique to each view, which creates photometric inconsistency, leading to noise. Triangulation by laser striping is one of the basic techniques used to reconstruct 3D shapes from as early as 1980s. It basically involves a laser beam swept across the scene or the object and a camera which photographs the beam. A laser beam or a laser dot can be photographed, and the location of the dot in the image allows triangulation. To this end, when the system is calibrated, we get the distance to the object. Laser triangulation can be very precise, down to the tens of microns. However, it only allows measurement at smaller distances, up to meters. While the laser 3D scanners discussed previously can be widely used, it requires to translate the laser plane across the object manually and needs hundreds of images to build a complete model with acceptable detail. It could be argued that the scanning process is inefficient, in the sense that only a very small set of pixels illuminated by the laser contribute to the scan in each image, and the rest are mostly ignored. A question arises of whether it is possible to achieve more efficient scanning by eliminating the mechanical motion required to the laser slit scanner. On the contrary, a structured light scanner replaces the projected laser line with a data projector capable of displaying two-dimensional patterns, covering a much larger object region and generating a 3D model containing all the points being simultaneously illuminated by the projector and visible from the cameras. More information is extracted from each image, thus reducing the number of images required and the total scanning time. Structured light scanners became highly popular in the recent years, mainly because of their low cost and wide availability of quality data projectors and cameras. Assuming no lens distortion, the projector can be used to display a single column or row of white pixels translating against a black background. The image distorted by the geometry of the scene can be recorded by the camera. However, as many images as columns or rows on the projector would be required in order to assign the correspondences between camera pixels and projector columns. After establishing the correspondences and calibrating the system, a 3D point cloud is reconstructed using ray plane triangulation. However, a simple strategy like this does not fully exploit the projector. Since we are free to project arbitrary 24-bit color images with most projectors, one would expect there to exist a sequence of coded patterns, besides a simple translation of a single stripe, that allow the projector camera correspondences to be assigned in relatively few frames. A simple binary structured light sequence was first proposed by Postdamer and Altschula in 1981. As shown in the animation, the binary encoding consists of a sequence of binary images in which each frame is a single bit plane of the binary representation of the integer indices of the projector columns or rows. In practice, one may use 20 images to encode 1024 columns or 768 rows. Considering the projector camera arrangement as a communication system, then a key question arises: what binary sequence is most robust to the known properties of the channel noise process? At a basic level, we are concerned with assigning an accurate projector column row to camera pixel correspondence. Otherwise, triangulation artifacts will lead to large reconstruction errors. Gray codes were first proposed as one alternative to the simple binary encoding by Inokuchi in 1984. The key property of the gray code is that two neighboring code words, such as neighboring columns in the projected sequence, only differ by 1 bit. That is, adjacent codes have a Hamming distance of 1. As a result, the gray code structured light sequence tends to be more robust to decoding errors than a simple binary encoding. To decode the structured light sequence, one needs to decide whether a given pixel is directly illuminated by the projector in each captured image forming that sequence or not. This sequentially sets each bit in a sequence of bits corresponding to the projector column or row index. To actually decide whether the pixel is directly illuminated by the projector, one basically compares the brightness of the pixel to a certain threshold. While the threshold may be set globally, in practice a single fixed threshold results in decoding artifacts, and a variable per pixel threshold can be used.
First, the structured light setup is being mounted on a tripod. Then the system is ready to function, but it needs to be calibrated in order to determine the relative positions of the cameras. Now we can actually scan. To do this, we turn on the projector and position the object to be scanned on a rotating turntable. The actual scanning sequence projects stripes of white and black light on the object, and the reconstruction is immediately seen on the computer screen as a series of registered depth maps. Structured lighting projects patterns of visible or infrared light onto the object. The distortion of the pattern recorded by the camera provides geometric information. In fact, structured lighting has many advantages by projecting 2D pattern at once. It is possible to even perform in real time using devices such as Kinect version 1. However, structural light suffers from noise due to complex distance calculation and is also affected by indirect illumination scattered from directly illuminated points. It is also typically not real-time and ill-suited for dynamic scenes. Both slit scanners and structured lighting are ill-suited for scanning dynamic scenes. However, perceiving dynamic scenes is one of the major requirements for robotics, including mobile robotics and autonomous driving. In addition, due to separation of the light source and camera, certain occluded regions will not be recovered. In contrast, time-of-flight rangefinders estimate the distance to the surface from a single center of projection. These devices exploit the finite speed of light. Let us give a few definitions for this section. Radar, which is actually an acronym for radio detection and ranging, is a detection system that uses radio waves to determine the range, angle, or velocity of objects. All radar systems employ a signal transmitter that emits electromagnetic waves in the radio or microwaves domain, and a receiver, which reads reflected electromagnetic waves which encode information about the properties of objects. LIDAR predominantly employs infrared light from lasers rather than the radio waves. It is a method for measuring distances by illuminating the target with laser light, which is spatially coherent and allows to focus the beam of light into a single spot on the target. Time of flight is the measurement of the time taken by the object, particle, or wave to travel a distance through a medium. In the ranging context, TOF measures the time it requires for the reflection of the light to return to the sensor. A broad variety of time-of-flight sensors includes, for example, the well-known scanning LIDAR or time-of-flight cameras. The simplest version of a time-of-flight camera uses a series of light pulses or a single light pulse. In this case, the scanner emits a focused pulse of light and waits for it to return to a sensor. The time it takes for the light to return, multiplied by the speed of light in air, tells us how far the pulse traveled. Technically speaking, the illumination is switched on for a very short time. The resulting light pulse illuminates the scene and is reflected by the objects in the field of view. The camera lens gathers the reflected light and images it onto the sensor or focal plane array. Depending upon the distance, the incoming light experiences a delay. As light speed is approximately 300 million meters per second, this delay is very short. An object 2.5 meters away will delay the light by 16 nanoseconds only. This requires precise calculation of the time shift between the two signals. One approach to calculating the shift is to simply cross-correlate the reference waveform with the measured optical signal, and find the peak. Another approach is called amplitude modulation of a continuous wave. In this case, the laser is operating continuously, but the power of the beam is being modulated sinusoidally over time. After bouncing off of an object and returning to the sensor, the reflected light still has sinusoidal power variation with time, but it is now out of phase with the emitted light. By computing the phase difference between the emitted and reflected power signals, we can again compute round-trip distance to the surface. Both the time of flight and AM imaging radar systems can scan a scene by using mirrors to sweep the laser beam. With current technologies such as nanophotography, we can in practice visualize light sweeping over the scene. In this setup, the theoretical best-case time resolution is calculated at 69.4 picoseconds from the hardware specs. In this scene, multipath effects can be seen in the glass vase. In the early time slots, bright spots are formed from the specularities on the glass. Light then sweeps over the other objects on the scene and finally hits the back wall, where it can also be seen through the glass vase at 8 nanoseconds. Light leaves first from the specularities at 8 to 10 nanoseconds, then from the stuffed animals. The time slots correspond to the true geometry of the scene. Light travels 1 foot in a nanosecond. Times are the round trip. Let us go to the lab again to demonstrate the functionality of our Leica 360 BLK time-of-flight imager. The sensor is started by invoking the command from an iPad. It calibrates itself and performs 360-degree color shooting. It then performs laser scanning by projecting the laser through a system of rotating mirrors. The entire scanning process takes up around 1 minute. The resulting scans are viewed in a point cloud form on an iPad. LIDAR range scanners is a time-of-flight devices which use laser illumination instead of incandescent or fluorescent light. This is because lasers can be focused tightly over very long distances and because lasers have an extremely narrow radiation spectrum. The first property allows us to make very tight beams or narrow stripes to improve the resolution of our systems. The second property means that we can achieve relatively high immunity to ambient illumination in the environment. Covered by an optical filter tuned to pass light only at the laser's wavelength, the sensor effectively sees nothing but the reflected laser light. Commonly, LIDAR scanners are engineered to employ a system of rotating mirrors, like the one shown in the right, that allow for the laser beam to sweep over the scanned scene. Perhaps the most prominent application of LIDAR sensors is in the autonomous driving context, where they support perception for self-driving cars and other mobile robots.
As you can see here, the single light photon is emitted from the sensor, hits an object like a tree, and bounces back to the LIDAR sensor, at which point the data from the light photon's travels is recorded. It is measuring distance and time. The amazing thing about this is that it works for non-stationary objects in real time, such as pedestrians, bicyclists, and other cars. Because LIDAR is its own light source, It can even see at night. This is an advantage over cameras, which have trouble in darkness. A good LIDAR has from 8 to 128 laser beams to measure the environment. The laser beams in the LIDAR emit billions of light photons per second at 360 degrees in order to completely see the surrounding world. It is pretty amazing that billions of data points and calculations are happening in real time. This allows the car to see and keep drivers, occupants, and all other road users safe. It is kind of like spraying paint all over the surrounding environment in order to highlight objects, make them recognizable, and show movement.
However, recently LiDAR-based sensors have been demonstrated in the personal 3D scanning context, where they're able to capture real large-scale objects. For example, this truck has been reconstructed in near real time on iPad 12 Pro tablet. Radar-based active lighting computes time taken by radio waves or laser pulses to travel to and from objects. Its advantages include the possibility of operating in real time and very large scale, such as hundreds of meters or even kilometers. LiDAR is also immune to ambient illumination, which makes it day and night enabled. However, in real time, the reconstructed point cloud of measurements is too sparse for 3D scanning. In the autonomous driving context, LiDAR also is prone to reflections from dust, smoke, snow, or rain, which also limits its applications.
Thank you.